I'm sure most of us have heard and know the basics about what general electricity is, the stuff that we use when we plug our phone into a wall or listen to music, um, the outlets. What we have with regular electricity is charges that are constantly moving. However, what we're looking at here with static electricity is charges that don't move freely through an object or through a conductor, but rather build up until they can no longer stay in that same area, at which point we might get a static discharge or a jump that electricity has to be released. So static electricity, like it sounds, is where we have very static, stationary charges building up until they can no longer be contained. When we refer to electricity, we're generally referring to things that are really good conductors that allow those charges to move easily from one location to another, such as metals. With static electricity, the things that are going to best help us to build up static electricity are things that are going to hold those charges in place. So here we're talking more about insulators, plastic, rubber, glass, things like this. In terms of static electricity, we've got three main methods that we can transfer the charge from one object to another. The first method is by contact, also known as conduction. So here we're dealing with things that touch or rub. One of the best examples, probably the one that we've all done before, is you rub your feet across the carpet. And if you rub your feet across the carpet long enough, you're building up those static charges in your body, so that the next person that you touch, you're able to transfer that charge from you to the person. So I've conducted that electric charge from the carpet to my feet, and then I can conduct it further from me to somebody else or something else, and that's where we see that shock. The second method that we have for transferring a charge is what we call induction. When we induce something, we're creating it, we're forcing it to happen. So induction will occur when a charged object comes into contact with a neutral object. So that charged object is going to force the neutral object to develop a charge. A good example is if I take a balloon and I rub that balloon. By rubbing that balloon, it's going to pick up negative charges, electrons, from whatever object I rubbed it on, like, say, somebody's hair. And now if I take that balloon and I bring it near a wall, that wall is normally very neutral, and it's going to stay neutral. But the electrons in that balloon are going to push, they're going to apply a force to repel the other electrons further away. This is going to cause the positive charges, those protons, to line up closer to the front of the wall. And as a result, I now have negatives and positives attracting each other, while the negatives and negatives are repelling each other. So I've created a charge in the neutral wall by bringing another charged object nearby. The third method that we have for transferring a charge is probably the most commonly seen. It's static discharge, or better known as a spark. So here we're looking at that visible spark that you have when you transfer your charge from one object to another, or something like lightning. Here the charges have built up in the atmosphere and in those clouds, and they're going to try to get to something that is, again, fairly neutral, such as the ground. And so they're going to discharge or shock their way down, and we'll see that actual spark. So static discharge is something we have to see. There are several rules that are going to apply to electrostatics. The number one rule that we have, as with most of our laws in terms of physics, is the law of conservation. Here we're talking about charges as opposed to mass or energy and things like that. But the charges that we have are transferred from one object to another, but they're never created or destroyed. Now, when we talk about these charges being transferred, if we think about what we know about an atom, in an atom we've got that tightly packed nucleus with those positive charges and our neutral neutrons. And they're holding very tightly to each other. It takes a very strong force to keep those similar charges from repelling each other. And scattered around the outside of that atom, we have our electrons. And those electrons are also repelling each other because they have a similar charge. Now, in terms of transferring a charge, it would be very difficult to take a charge from the center and pull it out. So transferring a proton would be very hard to do. It would take a lot of energy. But because the electrons are already scattered wide around and they are not as tightly bound, it is easier to move an electron off than it is to move a proton off. So that is one of the reasons, or one way to remember, that the electrons are the things that are actually transferring. They're the outermost part, and they're the ones that would take the less force or energy in order to actually move and release. A couple other of the rules that we have for electrostatics are things that you've probably heard before, and I've already kind of alluded. So one of the common ones is if I have two balloons, and one's positively charged and one's negatively charged, and I ask you what's going to happen, you're probably going to say opposites attract. So they come together. Similarly, if I had two balloons and I had them both the same type of charge, so in this case both negatives, we could probably assume that if opposite charges attract, then like charges repel, and these would push apart from each other, which feeds into some of our rules. So here are the kind of the common and typically seen as some of the most important rules that we have. And the first one being that all charges are surrounded by an electric field. And that field is supposed to push or pull on objects that are near it. So 1 and 2 kind of go together. We have our charges surrounded by a field, and that field is going to apply a force to anything that comes near it. So in the case of our balloons that we had a second ago, when we have one balloon that's charged up, and we bring another balloon nearby, this first balloon is either going to push or pull accordingly depending on the charge that's there. Again, opposites attract and like charges repel. Electrostatic forces are fairly strong, especially when we consider them in relation to gravity. So you've probably seen before where you could take a balloon, rub it on your head, and then if you work hard enough, get it to stick to a wall. Well, gravity is trying to pull that balloon down. But it's not falling, and if and when it does fall, it falls very, very slowly. It doesn't fall at the same rate as every other object, telling us that this force of gravity, by comparison, is fairly weak. So what is holding it up? Well, the force that's holding it up is actually our electrostatic or electromagnetic force, keeping it tight to that wall, keeping it from wanting to slide down. So I can see from that idea that this force must be much stronger than the other.